Today's topic is superconductivity. We have earlier discussed that ceramic materials have a wide spectrum of electrical properties starting from superconductivity to insulating properties. We have discussed semiconductivity and insulating properties earlier. Today we will take up the superconductivity. First of all, what is superconductivity? How do we define this property? This is basically a statement of how we can describe the superconducting behavior of materials. This is a particular property of specific group of materials, not only of course ceramics. There are a large number of non-ceramic materials which do possess this particular property. So, this is a particular property of a specific group of materials that lose their electrical conductivity, or in other words it becomes a zero resistance state when cooled below a specific temperature. And under normal condition, normal temperature and pressure, they do not behave in this manner, but only when they are cooled at a very low temperature, normally below 100 K, then this material is supposed to be superconducting, so that the resistance becomes almost 0. For all practical purposes it becomes 0. Only a limited number of materials demonstrate this property, not all materials demonstrate. All materials when cooled do not possess this property, only specific materials become superconducting at a very low temperature. This particular property was discovered more than 100 years back, precisely in 1911 by a scientist named Kamerlingh Onnes, who was of course awarded Nobel Prize in 1913. So, it has been going on for a long time. The property is known for fairly long time, even though we will see later many of the theoretical understanding is still lacking. This is the typical resistance curve. We have seen earlier how the metals behave. We will see some of the curves today also, but this is the normal behavior of a metal. Resistance decreases as we decrease the temperature, and it tends to be 0. In fact, it does not go to 0 even at 0. If you extrapolate, it has always a residual resistance even at absolute 0 temperature. But there are a group of materials when cooled up to certain point, very close to 0 of course, then suddenly all on a sudden the resistance become 0, it comes to 0. It is not a gradual change, it is a discontinuous curve here. So, there is almost a vertical line at certain critical temperature, and that is called the superconducting critical temperature. So, this is the typical resistivity versus temperature curve for a superconductor. This is a non-superconductor versus superconductor resistivity curves of two different metals. One is silver, another is tin. As we have discussed earlier, silver is one of the highly conducting materials, the elements, and it has been used as a conductor in many different sophisticated purposes. However, tin is not that conducting, its resistivity is relatively high, whereas so far as the superconducting property is concerned, silver does not show any superconducting property. Even at 0 degree Kelvin, you have a residual resistance, it does not go to 0. Whereas, a superconducting element like tin, which has a superconducting transition at a slightly higher temperature or between about 2.5 to 3 degrees Kelvin, you have a superconducting transition, and suddenly the resistance goes to 0. So, this is a typical again a superconducting behavior of elements. And so, although it is highly conducting in the normal condition, but it does not have a superconducting property. So, it is related to something else, its structure, its electron phonon interaction and so on. Few other statements. The temperature at which the normal conductor loses resistivity becomes superconductor. That is the definition of the critical temperature. The Tc, that is the Tc is the temperature at which normal conductor loses its resistivity and becomes superconductor. That is how the Tc, the critical superconducting critical temperature, has been defined. The temperature is fixed for a specific material. So, it does not vary, it does not depend on the way it is cooled or the rate of cooling or rate of heating, it really does not change. So, it is very specific and a characteristics of a particular material. So, of course, for different materials the temperatures are different, as you will see later. It is reversible, that means once you cool you have a zero resistance state, but if you come back or heat it up and cross the transition temperature, once again it becomes a normal conductor. Okay. So, it is a reversible phenomena. So, it is basically a reversible transition which takes place at specific temperature. Very good electrical conductors, that which have been mentioned earlier. The very good electrical conductors are really not necessarily superconductors, most of the time they are not. Okay. So, for example, the three most conducting elements like copper, silver and gold, they do not become superconductor even if you cool to very close to absolute 0. So, these are some of the characteristics of superconducting transition or superconducting phenomena. So far there are two categories or two subgroups of superconducting materials. One is normally called low temperature superconductor and the other in high temperature superconductor. Of course, till very recently about mid of 80s most of the superconductors are basically low temperature superconductors, till some ceramic superconductors were discovered around 1986, and that is the distinction. Now we have a very distinct group of superconductors which are mostly ceramic superconductors, oxide based superconductor and they are called high Tc superconductors compared to the low Tc superconductors which are either elemental superconductors or intermetallics. So, some examples of the, to start with, the low temperature superconductors. These are few examples of low temperature superconductors. As we have mentioned, mercury was the first element to be discovered in which the phenomena of superconductivity was observed, and then few other elements like tin and lead also have been discovered later, that they have also the superconducting phenomena or they behave as a superconductor. The superconducting transition temperatures has been given on the right. For example, tin has 3.72, mercury 4.15, these are all degree Kelvin, lead is 7.19. So, these are few elemental superconductors having a very low transition temperature. Later on quite a few intermetallic compounds have been also found to be superconducting property. The important ones among them is niobium titanium, it is an intermetallic compound and having a transition temperature of 10 degree K, niobium tin, another intermetallic compound, both of them of course niobium is a common element present. So, either it combines with titanium or tin, they do have superconducting property, and this temperature is slightly higher 18.1. So, one of the highest one can say. There are other, we will come to that. However, in 1986 the first oxide based superconductors were discovered, and till that time niobium germanium was the highest superconductor, although it has been categorized under high Tc superconductors, but really not high Tc, except they have a much higher transition temperature than the rest of the groups shown earlier. So, the first high temperature superconductor actually in effect it is here, but in between this is the first observation of a superconducting phenomena in an oxide based material, lanthanum barium cuprate, lanthanum barium copper oxide. It was observed by Bednoes and Muller and in 1986, and in the next year they were awarded the Nobel Prize, because before that there was no question of having superconducting phenomena in oxides. Nobody could really think that some of the oxides can also show superconducting behavior. Now, within a few months, in fact, the same family of oxides where lanthanum has been replaced by yttrium, and immediately there is a big jump in superconducting critical temperature from 34 K, it immediately jumped to about 90, there is a big jump there. So, in between, otherwise there were gradual changes with different materials over a period of 75 to 80 years. Then of course, once the oxides could be found to behave as superconductor, then there were various different other oxides came in, complex oxides, many different substitutions took place, and within a 10 years or so the critical temperature could be raised. At that point of time, of course, there was a high expectation that superconductivity can be observed even at room temperature or higher than room temperature, but that has not been so. So far there is no room temperature superconductivity available, but the transition temperature has certainly increased quite significantly from around 4 degree Kelvin to more than 125 or 130 degree Kelvin. That is a big jump, no doubt, but it took more than 100 years of research to come across such a phenomena. So, we will discuss some of these things later on, some more details of these compounds. So, these are basically ceramic superconductors. One can classify them as ceramic superconductors or high Tc superconductors. Well, if you look at the structural features of these oxides, ceramic superconductors or high Tc superconductors belong to a cuprate basic copper oxygen block or cuprate class of superconductors, and they have a mixed copper oxide together with copper oxides together with few other cations. So, there is a substitution of different other cations or addition of different other cations in addition to copper oxide. Most of them may be viewed as intercalation of perovskites and rock salt blocks. So, it is a complex structure again, and you have a perovskite block as well as rock salt blocks, and the rock salt block is composed of AO type oxides, like A can be bismuth or thallium layers, whereas perovskite blocks can be CuO2, and M can be represent an M. Okay. So, it is a in CuO2 you can replace or add other oxides like calcium and yttrium. So, that forms the perovskite block. The common intercalation region is BO, that is B is lanthanum, strontium or barium layers being structurally related to both the rock salt and the perovskite blocks. So, one hand you have a perovskite block, another hand you have another side you have a rock salt block, and in between you have a oxygen layer, oxide layer of either lanthanum, strontium or barium. So, these are simple description, very simplified description of the structures, the ceramic structure, superconductor structures. Well, we will come to this maybe at later. Basically, how the superconductivity arises here. Of course, we have to have some electronic transport, and basically the transport takes place in a layer form. It is not a isotropic material. So, in some direction superconductivity is predominant or prevalent, whereas in other directions, particularly along the z direction, there is hardly any superconductivity, whereas the xy direction in the layer the superconductivity is prevalent. So, the cuprate layers are electronically active part of the structure, so and also responsible for the transport of the superconducting charge carriers. So, the superconducting charge carriers actually moves in a layer structure or in the xy plane, whereas in the z plane or z direction there is hardly any transport. So, it is highly anisotropic property, and in fact, in many of the other superconductors also one can find this kind of behavior. The adjacent blocks act as the charge reservoirs by providing the necessary doping with free charges. So, the charge carriers actually is provided by the adjoining blocks, which we have mentioned earlier. So, such charges have been recognized to be constituted by holes, while in normal superconductors, that means low temperature superconductor, it is the electrons, electron pairs to be more precise. Electron pairs moves, and those are the charge species which carries the charge or give rise to the conduction process. Whereas, in case of high temperature superconductors, it is believed that not the electrons, but the holes are more predominant charge carriers here. So, that is one of the difference between the high temperature superconductor, oxide based superconductors or ceramic superconductors compared to elemental or intermetallic superconductors, which we have discussed earlier. Well, this is what we have described just now, and this is a simplified form of the particular structure, that is the yttrium barium copper, yttrium barium cuprate, and that is the formula. Sometimes it is called 1, 2, 3 compounds because of the ratio of the elements present. Yttrium is present in only one element, one atom. This is 2 atoms and this is 3 atoms, copper is 3. So, sometimes they are called 1, 2, 3 compound, or also it can be called YBCO, YBCO. Okay. So, that is how it has been described in the literature, and this is the formula. It is a oxygen deficient oxide. Okay. It is an oxygen deficient oxide, although oxygen deficient oxides are supposed to be electronically conducting, but in this case it is a very peculiar situation where you get actually whole conductivity rather than electronic conductivity. Of course, there is little bit of controversy about that. So, it was discovered in 1986 in fact, not in 87, but 87, sorry, this is fine. This is not the lanthanum barium copper, this is yttrium barium copper. This was discovered in 1987 by Paul Chu, and it is as mentioned earlier, its transition temperature varies between 90 to 95 K. Okay. And there are some other properties which will be more relevant when you discuss the other aspects of superconductivity. For the time being, one can say that it is a type 2 superconductor. What is type 2 superconductor we will discuss in few minutes, and there is a critical magnetic field as well as critical current. So, this is the order of the current one can expect a superconductor of this type can carry without destroying the superconductivity. These are the typical blocks of different blocks we have described just now, and then you have this is barium and this is yttrium and this is cuprate block. So, this is the cuprate block where you have oxygen and copper, and one can see particularly at the which are facing the yttrium ions, there is some distortion of the oxygen. So, there is they are not completely flat planes or the crystallographic planes are not real flat planes, or but there is some distortion here, okay, both on this side as well on this side. So, this is what basically a kind of distorted perovskite kind of structure, and because of the distortion you have different blocks where one can get a symmetry of rock salt as well. These are the ionic sizes of these different elements present here: copper, yttrium, barium and oxygen. Okay. We will come to these figures later on. Now, this is a comprehensive picture of how many different compounds have been discovered so far, and how over a period of 100 years how the transition temperature has improved in different compounds. This is the elemental superconductors which we have mentioned earlier: mercury, lead, then niobium, niobium nitride, niobium tin, vanadium, silicon, niobium germanium and so on. And there is another group of materials which has also been discovered at different points of time, but their transition temperature are very, very low. Okay. There is hardly any change of within 5 degree Kelvin. So, there are even C and T, as some people have reported that there is superconductivity, the carbon nanotubes, and then there are more complex compounds, basically intermetallic compounds. They are not oxides, okay. These are carbides. Then you have potassium C60, all kinds of different compounds have been shown to be superconductor, but the main group is here, which are of more industrial or application related materials. The highest in this area elemental or intermetallic compounds is magnesium diboride, okay. And then very recently after 2006 2007 this compound has also been observed, a intermetallic compound of iron and arsenic, that is the highest Tc is more than slightly more than 50 K. Okay. However, there is a bifurcation here. These all are oxides. These groups, the oxides first started with barium, lanthanum, barium, copper, and then immediately by changing the substituting lanthanum by yttrium, a very strong, a very large jump has taken place. So far as the Tc is concerned, from 35 to 34, 35, it has gone to about 90, and then there are few other compounds in this range which has been observed to be slightly higher Tc, and almost 150, one has reached 150, but this particular one has reached more than 150, but not at normal pressure, at about 30 gigapascals. So, pressure also has an effect on the transition temperature. Otherwise, normal pressure it is around 130 to 150. So, magnesium, thallium, barium, copper, copper oxide, calcium. So, there is a lot of substitution in the basic cuprate structure. So, it started with these cuprates, and then more and more substitutions make the structure a little more complex, and of course, you have one increased Tc. So, that is a very good sign that we are still on the path of increasing the Tc, and maybe one can expect at some future time one can expect a room temperature superconductor with some oxides. So, ceramic superconductors are believed to have a great future so far as the Tc is concerned, but there are many practical problems, some of which we will be discussing later on. Well, there are certain in addition to critical temperature, there are few other behavior must be understood and we remember. For example, there are two critical parameters, one is the critical and persistent current. Okay. Since we have seen that superconductors are having a zero resistance, so a zero resistance result in very high current. So, a very small applied voltage will give you very high current. In effect, or theoretically one can have an infinite current. So, that is the peculiar situation or very interesting situation for superconductors. So, high current however induces high magnetic field. Okay. So, high current means high magnetic field, which in turn may destroy superconductivity. That is also another consequence, that once you have a high current there will be a high magnetic field, and this magnetic field has an effect on the current itself or the superconducting behavior of the material. The induced critical current is given if you have a coil of superconductor. So, once you apply an electric field and a current sets in, that current will continue to be there even in the absence of the electric field. So, even after the withdrawal of the electric field, you can have a current flowing once it is induced in a superconducting coil of this nature. So, this is what we call the persistent current, the steady current which flows through the superconducting ring. It has to be a complete ring, of course, not a open circuit one, a complete superconducting ring without any decrease in strength even after the electric field is withdrawn. So, once a current sets in by applying a small electrical field, one can withdraw the electric field, but the current continues to flow, and that is what we call the persistent current in case of a superconducting ring. Now, this critical, there is a value of the critical current, induced critical current is depending on the Hc actually, and also depends on the diameter or the radius of the ring. So, Ic is equal to 2 pi r Hc, Hc is the critical field above which the superconducting property may be lost. So, that is what the critical current is. We will find out or discuss little more details what is those values are and what exactly it means. So, there is a persistent current. What the more important point in this slide is basically the persistent current, the steady current which flows through the superconducting ring. So, that is a very important phenomena and observation, that since there is zero resistance, a very high current flows in compared to many other conductors. Obviously, the current is much higher at a much lower voltage, and not only that, even when the field is withdrawn, one can still have a persistent current in a superconducting coil. So, that is another very important phenomena in superconductors. Then we have just now mentioned that there is a effect of magnetic field. In fact, high current produces magnetic field, and then the same field also tries to destroy the superconductivity. So, it is a self controlling phenomena to some extent, that so that the current really does not go to infinity. So, there is a realistic current which flow, a real current which flows and which is kind of a steady current. The critical magnetic field is a critical magnetic field is required to destroy the superconducting property. So, the value depends on the temperature below the critical temperature. Obviously, above the critical temperature there is no question of superconductivity, but even below the critical temperature there is a possibility that the superconductivity can destroy itself, and that depends on the what kind of magnetic field it generates and what kind of magnetic field it produces either by itself or a magnetic field is induced from the outside. So, depending on what kind of magnetic field is generated, so there is a critical magnetic field which is Hc and which can be expressed in this manner 1 minus T by Tc square multiplied by a constant term which is specific to that particular material, and H0 is the critical field at T equal to 0. Okay. We will see the next curve what exactly it means. So, this magnetic field, that is a critical magnetic field even below Tc. Okay. It does not mean that at Tc or below Tc, the temperature below Tc all the time a superconductor will remain as a superconductor. That superconductivity can be lost depending on how much current is flowing and how much magnetic field it is generating. So, we can go to the next slide by saying this is the relationship between the Tc and the magnetic field. So, this is the critical magnetic field, of course. This is the critical magnetic field. That means, at Tc, this is the critical temperature, exactly at Tc you may not get a very high current, because the Hc, the critical magnetic field is very low, whereas if you go down the temperature critical magnetic field increases and finally reaches the highest value at T equal to T0. So, this is the magnetic field. Okay, this is the magnetic field which below which it is a superconducting state. So, it is not our definition of superconductivity may have to be modified to some extent. So, you have to introduce also it is not the temperature effect only, the magnetic field effect is also important. So, only at 0 magnetic field we have seen at a particular temperature there is a sudden change of resistance and it becomes 0, whereas if there is a finite magnetic field applied, then the Tc further decreases. Okay. So, this area, the H versus T curve, this area is actually a normal state. So, any material which has a normal Tc with 0 field here, the Tc may decrease to this provided the magnetic field is higher here. Okay. So, there is a relationship between temperature and the magnetic field which you have given here. The critical field is H0 1 minus T by Tc square, and that is what is H0 here shown from this curve. This becomes H0. So, at T equal to 0, this is actually H0, right, and for all this either T and Hc there is a critical current. So, the critical current also decreases as we come closer to the Tc, but critical current increases as we go beyond Tc or towards the 0 degree Kelvin. So, there is a relationship between the temperature, the magnetic field and Jc. Jc is termed as the critical current which can flow in a superconductor without changing it to the normal state. So, otherwise a superconductor will becomes non-superconductor if those values are exceeded. These are some of the values of critical field in low temperature superconductors. For example, niobium, it is only millitesla at 0 degree Kelvin. This is Hc at 0 degree Kelvin is only 198, that means this value is about 198 millitesla. Lead is about 80.3 millitesla, and tin is about 30.9 millitesla. So, for different materials these values Hc values are different. So, if we exceed this particular value, the material becomes non-superconductor irrespective of the temperature. And therefore, from this Jc is the maximum current a superconductor can carry at a temperature less than Tc. These are the in fact, this is more or less similar variation also you will get with Jc. That means, as you decrease the temperature you have a higher Jc. If you are closer to the Tc, then you have a lower Tc. So, that is the maximum current which a superconductor can carry without changing over from the superconducting state to the normal state. So, if you the current is more than this value, the superconductivity is lost. So, there is a relationship between temperature, magnetic field as well as the current which can carry. Well, there is another very important property of a superconductor that is known as the Meissner effect. When a superconductor is placed in a magnetic field at T less than equal to Tc and H less than equal to Hc, flux line, the magnetic flux lines or the lines of forces are fully excluded from the superconducting material. That means, if it is a normal material, then either paramagnetic, let us say paramagnetic in particular. So, the lines of force actually crosses through the material. So, this ring is actually or it is a sphere or a plate, one can say it is actually is supposed to be a superconducting material or there is a superconducting transition. So, in this state there is no this is a normal material, not a superconducting material. So, the magnetic lines of force crosses or penetrates through the material. However, if this material gets transformed to a superconducting material, the situation becomes like this, that all magnetic lines of force are excluded from this material, they repel. Superconducting material repels all the magnetic lines of force. So, it goes bypasses it and then goes. So, this is what we call a magnetic lines of force or flux lines are fully excluded, meaning a perfectly diamagnetic behavior. This is what happens when there is a diamagnetism. Diamagnetism has been as defined the susceptibility. The susceptibility is less than 0, is negative, but it is not always 1. So, a superconductor other diamagnetic materials the value is not exactly -1, it may be slightly more than that, but it is minus, it is sorry it is but it is negative, but close to 0. Whereas, in case of superconductor the value is exactly -1, and that means a complete exclusion takes place. In other diamagnetic material some lines of force, a fraction of lines of force can go through or penetrate through the material, whereas in a superconductor nothing penetrates, and that is what it is called a perfect diamagnetism. And however, flux line starts penetrating as T is more than Tc. So, this happens when it is completely superconductor, but if the temperature goes beyond Tc, then of course, the flux line starts penetrating and it does not remain as a perfect diamagnetic material. So, that is also another important aspect of superconductivity. So, this is particular effect of the behavior of diamagnetism or the observation of diamagnetism in a superconductor is known as the Meissner effect according to the scientist who discovered it. So, the realistic definition with this discussion, because there is a strong correlation with the magnetic field, and a better definition of superconductivity is that not only it must have a 0 resistance, the rho must be 0, but also x, the magnetic susceptibility should be -1. So, these are the two parameters fully describes the superconductor. A superconductor must have a 0 resistance as well as a susceptibility of -1. So, these are how one can modify our definition to some extent of superconductivity. Now, with this background, let us try to classify the whole range of superconductors on two other subgroups from different angles, not just from TC point of view or high TC or low TC. These are how it behaves in presence of magnetic field. There are two types, they are called normally called type 1 and type 2 superconductors, and their magnetic behavior is the following. This is what is type 1 superconductor. What has been plotted here is the magnetization against the magnetic field, and then you can once again see two different regions. One is the normal region and there is the superconductivity. This is at a particular temperature. Okay. This is at a particular temperature. This is what happens. Of course, below TC. Below TC, if you have a 0 magnetic field, the magnetization is multiplied by -1. As you can see, the magnetization when -h equal 10, it become m equal to -h, that means linearly proportional when h equal to hc, less than hc, sorry. So, this is hc value, critical value of hc, which we have discussed earlier. So, below hc m equal to the magnetization is proportional to the magnetic field, but with a negative sign. That means, it has a complete exclusion of the magnetic lines of force. The susceptibility is absolutely -1. So, it remains superconductor, therefore, it increases exactly proportional or exactly equal to the value of the magnetic field. At certain point it becomes 0. So, at Hc there is a critical magnetic field, suddenly the susceptibility becomes 0. Okay. So, from -1 its susceptibility drops to 0, or the magnetization which was equal to H, suddenly -H actually equal to 0. So, there is a sudden drop. So, once again just like TC, there is a transition, so far as the behavior of the material is concerned. At low field it is superconductor, whereas at high field it is non-superconductor, normal material. Okay. So, once again there is a transition, very sharp transition takes place. It is not a gradual transition, So, within this magnetic field it is superconductor. Of course, this kind of plots can be drawn at different temperatures. At different temperatures these values will be different, but there will be always below Tc there will be always a Hc critical magnetic field below which it becomes superconductor, above which it is non-superconductor. So, this is what we call the type 1 superconductor. The kind of behavior actually characterizes this particular type. That means, there is a sudden fall of magnetization and or the characteristics of the material, and exactly at Hc there is a sudden change of superconducting to non-superconductivity. There is another group of material, these are primarily observed in the whole range of different low temperature superconductors which we have discussed. So, in the low temperature superconductor this is another variety. In this case it is not a sudden change, it is not a sudden change like this, but a more of gradual change. The change takes place and finally of course, it becomes a normal. So, there is a superconducting state at low magnetic field and at a high magnetic field into a non-superconducting state, but in between is a kind of dual phase region. It is a kind of dual phase region, what we call a vortex region. So, in this region magnetic field there is slowly penetration of the lines of force. So, there is a gradual penetration of flux lines or lines of force, magnetic lines of force gradually starts penetrating into the material, and there is a gradual change of magnetization. Okay. So, unlike here there is a sudden change from a high value, suddenly it drops to 0, whereas in this case in type 2 superconductors they do not suddenly change. It should have, if it is a type 1 superconductor, it would have follow like this line and then suddenly Hc, but this does not happen, that is why it is given dotted. So, this does not happen, it happens only in type 1, whereas in type 2 this particular phenomena does not happen, instead it follows this curve or this straight line. So, this is again a straight line behavior, and as if you have a superconducting phase, non-superconducting, purely superconducting phase, purely non-superconducting phase, and then this is a mixed phase. This is basically a dual phase in terms of the phase diagram kind of thing. So, there is a, and this particular area, this particular region between this value of H, this value of magnetic field and this value of magnetic field, it is called vortex region. So, gradual penetration of the magnetic lines of force or flux lines do gradually penetrate into the material. As a result, you have two different critical magnetic fields. Instead of one critical magnetic field called Hc, here you have two different critical fields, one where the penetration starts and the magnetization drops from -1. So, this is called, the lower one is called the Hc1, and I am sorry, I think there is a mistake, it should be Hc2. This would be Hc2, this is not Hc1. This is Hc1 and this is Hc2. Okay. So, there are two critical magnetic field here, one is Hc1 and another is Hc2, whereas in type 1 there is only one critical field, one magnetic field. This mathematical equations has been plotted here like this or described here. M becomes minus H when H equal to Hc1. Okay. So, Hc1 is equal, when this is there, the same equation is valid, equal to minus H. If it is between Hc1 and Hc2, this becomes this is not H, it is a different value of H. Okay. So, it has a gradual change with the slope. The slope has to be increased, has to be introduced. So, H is a function of H1, Hc1 and Hc2. H becomes a function of Hc1 and Hc2, and then if it is beyond Hc2, beyond Hc2 actually, if it H becomes Hc greater than Hc2, then it is 0. Here it is beyond Hc, it becomes 0. So, these are the comparisons, these are the intercomparison between the two types of superconductors. In fact, this is not type 1 again, this is type 2, this part is looks like type 1, but the whole is type 2. Okay. In fact, it should be corrected as type 2. The behavior is that of type 2, not type 1. Type 1 is this one and type 2 is this one. So, these are the distinction between type 1 and type 2 superconductors, and let me see what is next. Well, there are some characteristics of type 2. In fact, type 2 superconductors are more useful from practical point of view, because type 2 superconductors can carry much higher current densities, and therefore are more useful for practical applications, and they can be modified also to some extent. So, type 1, because there is a sudden change, the type 1 superconductors are not preferred, type 2 superconductors are preferred because there is a gradual change of, so there is no catastrophic failure. Okay. Even if the local magnetic field or local JC, the critical current increases for some reason, there should not be any catastrophic failure. In type 2, the catastrophic failure is less, chances of catastrophic failure is less, and therefore, type 2 superconductors are more preferred. Not only that, the current densities are relatively high. Hc2 strongly depends on the microstructure of the material. So, once you refer to the earlier picture, this value is not a fixed value, okay, for any particular compound or element. It depends on the many extrinsic properties of the material. So, one can modify, one can manipulate this curve, either it can be here or it can be there. So, this manipulation can be possible with type 2 superconductors, whereas that kind of manipulation is not possible with type 1 superconductors. So, Hc2 strongly depends on the microstructure of the material, particularly the presence of pinning centers. As you have said, between Hc1 and Hc2, the lines of magnetic lines of force starts penetrating. Now, it is the repulsive action which actually retains the superconducting property. So, if you can avoid penetration of the lines of force through the material, then the Hc2 will increase. Therefore, if you can modify the microstructure and design the microstructure in such a way that you do not allow the penetration to take place, magnetic lines of force to cross through the material, then there is a possibility that Hc2, both Hc or Hc2 and Jc can be increased. So, by an control of the microstructure of the material, other properties, not the intrinsic property, but the extrinsically the materials can be modified. So, the examples of pinning centers for the magnetic lines of force are like this: dislocation arising from cold working, particularly for metallic materials or intermetallic materials, where some amount of is not so brittle, but in general intermetallic materials are quite brittle. So, you cannot generate too much of plastic deformation. However, in elements one can introduce lot of plastic deformation, and plastic deformation means, we have seen earlier, it is basically the introduction of dislocations. So, by introducing plastic deformation or cold working the material, so that more and more dislocations can generate, and then dislocations can act as a pinning centers. So, it actually obstruct the penetration of the magnetic lines of force, and thereby increases the Hc2 value, the critical value. So, it becomes more useful. Similarly, you have large number of grains. So, in between the grains you have grain boundaries, those grain boundaries can also act as pinning centers. So, it actually helps in pinning the pinning the lines of force, and therefore, the penetration becomes difficult. Okay. Then you have precipitates. Precipitates, like fine precipitates in a matrix of one particular material, one can have a second phase as precipitates, and those precipitates can also act as pinning centers. So, by that kind of a manipulation of the microstructures, one can increase both the Hc value, Hc2 in particular, and then that also increases the current carrying capacity. So, Jc is basically provides us information what is the current carrying capacity of a particular conductor. Here this is very similar to other conductors. Every conductor has a current carrying capacity beyond which it heats up so much that there is a failure, there is a structure gets disrupted. So, every material has a current carrying capacity. So, in this case also for superconductors, Jc is the current carrying capacity, or that is, in other words, it is called the critical current. So, both Jc and Hc can increase in the presence of above pinning centers. We will see some actual values, how they can be changed from by introduction of these kind of pinning centers, right. So, the time is more or less up. So, we can finish this for the time being. We will continue the discussion in the next class. Thank you for your attention.